My name is Caitlin, and this is my lab report for Lab 1 on constant velocity. The purpose of this lab is to observe and compare an object that is moving with constant velocity, no net force or changing direction, and to compare it to a theoretical model calculated from a computational model. Newton's first law says that an object in motion stays in motion. Newton's second law says that the force on an object is equal to its mass times its acceleration. This means that the heavier an object is, the more force is needed to move or speed up the object. Lastly is the concept of constant velocity. This is where the net force acting on an object is equal to 0 and the object moves in a straight line at a constant speed. Some equations we will need for this experiment are the velocity update formula, which is the final velocity equal to the initial velocity, plus the net force over mass times the change in time. This equation is being used for this experiment because if the net force acting on the system is 0, then the velocity will not change. Two other equations we will need are the position update formula and the average velocity formula for the computational model. We can use the slope to determine the average velocity of the marker, and this position update formula is used in the computational model to update where the marker is at each step. The results of the lab showed that the experimental model confirmed that the object moved with constant velocity and experienced a net force of 0. The object used for this video was a marker, and in this experiment, the system is the marker itself. The surroundings include all the external factors that can interact with it, such as gravity, the normal force from the table that is being rolled on, and air resistance, though many of these are assumed to be balanced. This was observed using the software tracker, and the theoretical position comes from a computational model called GlowScript. The procedure begins with recording the marker rolling at a constant speed in a straight line. Then this video was put into tracker to see the observed position using video frames at set time intervals. After this, we use the computational model of GlowScript to see the marker's predicted position using the starter code given to us. The initial conditions for the position were determined using a scale reference and tracker. The initial velocity conditions were determined from the slope of the position versus time graph seen here for mass A. The initial position was 0.220 in the x direction. The initial velocity was later calculated using the formula from before, and the total time was 0.467 seconds. So the initial velocity was determined to be 0.468 meters per second in the x direction. Next, the initial conditions for the computational model in GlowScript were set to the net force being 0 because of the constant velocity. Delta T was set to 0.033 frames per second. The mass of the marker was set to 0.01. Even though it cancels out in the velocity update formula. The position update formula was used to predict the location and a positive slope was created. And then the time was updated as well, based on how long it took the marker to roll. Shown here is a position versus time graph of the markers predicted in experimental positions. From the graph, you can see they are very similar, which tells us that our experiment had a constant velocity with no acceleration and a net force of 0. This is consistent with Newton's second law. Some possible sources of error include friction and air resistance, which could slow down the marker. There could also have been some human error from the initial push of the marker or inaccuracies using tracker, such as where the center of mass was marked. If we flip the axes, so the negative x and positive x are swapped, the position and velocity values would have opposite signs. The slope would now be negative, but the shape of the position versus time graph would remain constant. The physics still applies and the net force would still be 0. When the net force is equal to 0, we cannot know exactly how many pushes and pulls are occurring, only that they balance each other. that results in a net force of 0, allowing for constant velocity. Forces like gravity and the push forward are still interacting but cancel out with friction. And in a conclusion, Newton's second law was supported because our actual and expected results were very similar. This indicates that the marker moved with constant velocity and 0 net force.